Hi, in this lecture I want to talk about a critical and important idea in linear algebra and machine learning, which is linear dependence and span. This goes with chapter 2.4 of the deep learning textbook that this course accompanies, so I highly encourage you to read that after watching this lecture. This also builds on ideas that we talked about in the previous lecture, where we talked about how we can view a system of linear equations geometrically in two different ways, and we're going to be using that second way, or the column picture, quite a bit in this lecture. So if you haven't watched that, go back and watch it before watching this. Okay, so let's go. So before we talk about these two ideas, we need to talk about something that will lead us to talk about these two ideas, and that's a question. And that question is, when is a matrix A invertible? And before I tackle that question, we need to kind of state one very important property of inverse matrices. So if we have some matrix A, and we have its inverse A inverse, so of course that equals the identity when you multiply them together, we know that this inverse matrix A is unique. For a given matrix A, it only has one possible inverse. So to make that concrete, if we have some matrix X times A equals I, and we have some matrix Y times A equals I, we know that X equals Y equals A inverse. Okay, so now that we know that there has to be only one inverse matrix for a given matrix A, let's go to kind of beginning to answer this question and begin to kind of lead to a discussion about these topics further down the line. So remember how we talked about systems of linear equations and how we can represent them in the notation AX equals B, where A is our coefficients matrix, X is our vector of variables, and B is our kind of right-hand side, right answers vector. So remember, we could instantly solve for all the values of X when multiplying both sides by the inverse of A, right? So we could do something like this. And of course, this would evaluate to the identity, so all we would get is this. So one thing we can realize from this, other than the fact that you can instantly solve for X, which we talked about before, one thing a little more subtle about this that we can understand is that since a matrix A can only have one inverse, and we look at this, since B can only have one value, so B is the vector of right answers, we can't change that. And since A inverse can only have one value, this only corresponds to one matrix, that means X can only have one value. If there are multiple solutions X to this system of linear equations, that means there would have to be multiple versions of A inverse, and that's impossible. So the other thing that we can glean from this is a matrix A is invertible only when this system has one solution. And we're going to talk about the geometric understanding of that right now. So first, let's take an example. It's going to be the same example we talked about last time. And I got the colors ready too. So say we have our first equation here, which is the same as last time. So you have some 2x plus y equals 3. And then we have another equation here. Colors are fun, but they're very tedious. So x plus y equals 2. So our solutions to that, as we talked about before, is x equals y equals 1, right? And we can always represent this in the matrix form, which will actually become more handy as we go along. So this is important. So our AX equals B form, like so. Like that, right? Okay, so now that we got that down, let's plot it in the column picture. So plotting these as vectors one more time, just like last time, and we're going to begin to answer this question, and we're going to begin to talk about these concepts here, just while I talk about this geometric kind of picture here. All right, so let's write out this Cartesian plane one more time. Let's hope I get it right. Okay, that's good enough. I'll take it. 1, 1, 2, 2, 3, and 3. Good enough. All right, so we have our Cartesian plane here. So now let's draw out those vectors. So what we're going to do is we're going to write this out as a vector equation as we did before, and we're going to kind of talk about our first new terminology of this lesson. So let's draw this out as we did last time as an equation of vectors. So we're going to take this first column here and make that our first vector. I'm going to draw that off right here. 2, 1. And this is multiplied by our first variable x. This adds with our second vector, so many colors, which is going to be 1 and 1. This multiplies by our variable y, and this equals our kind of right answers vector 3 and 2. So recall that we could plot these out, and this is all going to seem very familiar, and don't worry, it gets novel shortly. So that's going to be our first vector there, 2, 1, and then let's draw out 1, 1. So it's going to be going to here, so that's going to be like this. Let's make that a little better. There we go. Right, so those are 2 vectors, and remember, I'm not going to plot out the entire vector for 3, 2, I'm just going to plot out the point, which is going to be about here. Remember that if we plug in x equals 1 and y equals 1, which are systems to our solutions to the system, we would basically get this, and we wouldn't multiply this by anything, and then we would add this to the end of this, and that would result in our sum of vectors being this answer here. And you can actually see that being done algebraically. It doesn't have to be done geometrically. So say if x equals 1, y equals 1, that means you're going to be multiplying each of these vectors by 1, so they stay the same, and then you're just going to end up with 2 plus 1 equals 3, and 1 plus 1 equals 2. So that's going to equal the same thing. So we can see that it maintains algebraically. It's just nice to see the geometric intuition. But whatever. So we have that, and we already know this, and we already get that. We already understand that x and y are the solutions to this. But now we're going to call this a new thing. We're going to call this new left-hand side where we multiply a vector by some constant, and then we add that to a vector multiplied by some different constant. We're going to call this here a linear combination. So a linear combination is any sum, I don't know, v1, v2, times some constant c1, and then we add that to some other vector, w1, w2, times another constant, and then we can go on for as many as we like. That's a linear combination kind of in general form. But this is an example of a linear combination. So one thing that I want to point out is that we know that we can set x and y equals 1, and we result in something that gets you to this point. You can kind of imagine these vectors as directions, and we can imagine the variables as how much we want to go in that direction. And we can see that if we set those kind of magnitudes x and y to the right amount, we can get straight to the right answer, 3, 2. But the question I want to ask you is that if x and y can be any number on the real number line, then what are the possible points in this entire plane, this entire Cartesian plane, that we can get to? So if x and y can be anything, if x and y can be anything, what is the possible combinations of these 2 vectors that can result in what points? Like, can we get to this point if we set x and y to some particular value? Can we get to this point over here, or any point over here, or down here? What are the points we can get to when you set x and y to anything? And the answer to this question is that in this specific example here, if x and y can be any values, you can theoretically, not theoretically, you can actually get to any point in the Cartesian plane. So some point here, that's going to basically be the result of setting one of this to maybe a negative number to make it go in this direction, and then setting this, I don't know, some number that takes you up here. But I'm just saying getting to this point is possible. And the thing I want to talk about here, and this is our first thing that we talk about, span. The span of 2 vectors is the amount, not really the amount, but the set of possible points that can be reached as a linear combination of those vectors. So the span of the vector 2, 1 and 1, 1 is the entire Cartesian plane. And how we represent the entire Cartesian plane in letters is something like this, R2. So we say that the span of the vectors 2, 1 and 1, 1 is R2. Similarly, if we had 2 vectors that were 3-dimensional, so we were talking about the 3-dimensional space, and we could say that 3 vectors could totally span over, so if we had 3 vectors in 3 dimensions, and a linear combination of these 3 vectors, so let's make a really random quick example here. Just doing this super quickly. So we had another system of equations like this, and let's say that these now in 3D could span any point, a linear combination of these 3 vectors could span any point in 3-dimensional space. We would say that the span of these 3 vectors is R3 because now we're dealing in 3-dimensional space. But let's get back to reality here. So let's just quickly erase this. And I'm going to talk about one more thing here. Well, a couple more things, actually. You can probably tell by the length of this video, it's going to be a lot of stuff covered. But we already covered that with these specific vectors 2, 1, and 1, 1, our span is the entirety of R2. So we can access any point in the space. But another important thing to note is that for any point in the space, there's only one unique setting of x and y that get you to the exact point. And we see a good example with this with our right answer 3, 2. 3, 2, there's only one setting of x and y that get you to 3, 2. Same thing with this point here. There's only one setting of x and y that can get the vectors to point directly to this place. So for any given point in this place, in our span of R2, each point in the Cartesian plane can be reached by only one unique combination of the values of x and y. So that's a very, very important thing to understand. And that's kind of, you're always going to have the thing where you access the whole plane. In this scenario, when you can access the whole plane, then you're going to be able to get to it kind of uniquely. All right. So we know that we can set x equals 1 and y equals 1 and get to this point here. And the thing that we can glean from that is that since in the scenario, when we can get to any point in the entire surface, we know that each point is unique, that means the answer is unique, and therefore there's only one setting of x and y, and therefore again, that we get back to here, if there's only one possible setting of x and y that give you the answer, that means the matrix A is invertible. So that means the matrix 2, 1, 1, 1 is invertible because there's only one solution for x and y. All right, so now let's look at the case when there's no inverse for A. So there's no possible inverse for this. And when does that happen? Okay, so we got that. So now let's tackle another equation. Let's tackle another equation that's also simple, but is going to kind of display this other case. Okay, so let's use our colors again. So let's say we have some x plus 2y equals 3, and then we have another thing which says 2x plus 4y equals 6. So that's our new system of equations. So now let's plot these out again. So let's plot out the linear combination first, right? The linear combination represented by this. And let's get rid of this, let's not get confused. So basically our new matrix A equals B thing will look like this. So we're going to have some 1, 2, 2, 4, 1, 2, 2, 4. And then I have our x and y equals 3 and 6. So now let's write this out as a vector equation. So let's have some, let's start with red as we did before. So we're going to have some 1, 2, right, I believe it's actually, yeah, 1, 2. And this is multiplied by our x. And this is going to add to our second vector, which is going to be the second column of that matrix A, which is going to be 2 and 4. And this is going to equal 3, 6. So this is our new linear combination. So now our linear combination of the two vectors is this. So let's plot these vectors. And this takes time, but you can always kind of skip a tiny bit if you don't want to watch me drawing stuff. Okay, so let's relabel these to kind of fit. So we know that we have a 6 there, we're going to get bigger numbers. So let's say 2, 4, and 6. 2, 4, and 6, just kind of the cheat. Okay, so let's plot these two vectors here. So we have 1 and 2. So we have 1 and 2, so x equals 1, y equals 2, so that's going to be about here. Okay, and let's point our second vector, which is going to have 2 and 4. So it's going to be 2 and 4. And we notice immediately that these vectors are collinear. They occur in the same line, so well, this blue really overlaps with this red one, but they go in the same line. And that's kind of the first thing that we notice in the system. And lastly, let's point out where our answer 3, 6 is, which is going to be right here. So remember with last time is that with any setting of x and y, so our span was the entirety of the Cartesian plane. We could add and multiply the vectors in certain ways, well, not multiply the vectors together, but multiply the vectors by constants and add them in certain ways that would allow us to reach any point in the entire Cartesian space uniquely. But now we'll see that if we set x and y to any value, so let's look at the span of these two vectors. So if we can set vector x and y to any value, can we access a point over here? The answer is no, because what we're going to look at is the thing that allowed us before to get to different places around the Cartesian plane is that when we added a vector that went like this direction and went in this direction, it allowed us to go to different places. But since now they're on the same level, when we add them, if we added the blue vector to this red vector, we would just get on the same line because they're both going in the same direction. So if you were to add the vectors together, they would just take you in the same direction as well. And of course, when you multiply them, it just scales them anyways. So any combination of the values x and y will only keep you on this. So the span can be just represented as a single line through space, and this is supposed to be on the span. So there's only a span through space. Right, so we can only get to points along this line. Everything else is impossible. All right, so you might think, oh, luckily our answer is on the span, so we're good. Luckily, very luckily, our answer was on the span. If the answer, just very quickly, if the answer was not on the span, that would mean that the equations were inconsistent, and you can think about why that works. But let's just get back to this. So if it's on the span, we might count ourselves lucky. Luckily, it's on the span, so that means we can get to this point. But the thing we realize, and then we go back to this, is that A is only invertible when we have one value of x. But notice here that since they're in the same span, and you have two vectors on this exact same span here on this line, there are an infinite amount of values of x that can get you here. So say if you set the red vector to kind of a short number, so you kind of shortened it to here, so you multiplied it by something less than 1, so you got a little vector here. Then you could just add the blue vector on top of that to the number that kind of makes up for the rest of the distance. But then if you made the red one just infinitesimally longer, then you can make the blue one a different size and it'd still reach that point. So you can think about it, there's an infinite amount of combinations, an infinite amount of versions of these two vectors that will add and get to this point. So that means the vector x, there's an infinite amount of vectors of x. And that means in addition, if you keep following that line of logic, A is uninvertible. Okay, so that's a lot. So basically, just a very quick recap. In this scenario here, as opposed to our first scenario, the span of our two vectors, so the vectors that were the columns of our matrix A, the span of the vectors that were from the columns of A, and a term for this is the column space. So the span of the vectors that are the columns of A is called the column space of A. So the column space of A, the span of these two vectors is only a single line going through R2 space. And therefore, there's an infinite amount of solutions for any point, any kind of right answer located along that line. And in this case, the right answer is located along that line. So that means, we have a uninvertible matrix A. Hopefully that sort of makes sense. Okay, so one thing I just want to notice, and one thing that you can see, and one thing that you can kind of get from this, is that when we look at this matrix here, let's put these back into matrix form. So 1, 2, 2, 4. And I'm going to throw the other term in here. We still don't know what linear dependence was, but you just learned it. I just didn't give you the term yet. But if we put 1 and 2 and 2 and 4 in this matrix, we see that the second column here is just the first column times 2. So in this scenario, when we have one column can be combined, one column of the matrix A can be created by some linear combination of the other columns of the matrix A. We call this a linearly dependent matrix. And when you have a linearly dependent matrix, that means that matrix is uninvertible. So as opposed to our first example here, when we had the two vectors going in different directions, the second column of that matrix A was not a combination of the first. So in that case, we had a matrix that was linearly independent, or vectors that were linearly independent. But in this case, we have something that's linearly dependent. The first one is 2 times the second one. And if we go back to our equations, we can see that this whole inconsistency, this whole problem remains kind of consistent in our calculations, because we see that our second equation here is 2 times the first equation. So this second one, if we do elimination, really evaluates into 0 equals 0, and then we have our first equation, so we don't have enough information to solve the system. So you can see from this point that there's already an infinite amount of values for x and y that can satisfy our equation. So you can tell if a matrix is linearly dependent, or the columns of a matrix are linearly dependent at a glance, not really at a glance, but without doing all this geometric work. And therefore you can tell if a matrix is not invertible. Basically, as I mentioned, a matrix is dependent, or the columns of a matrix are dependent, when one column or two columns or all the columns are combinations of other columns. So let's look at a 3x3 matrix, and we won't have to deal with the geometric intuition here. So let's say we have some 3, 2, 3, 1, and then we have some 4, 5, 3, and then we have, say, 6, 8, 4. So this is our matrix, and we want to know if this matrix A has some inverse A inverse. So we could kind of go through the whole geometric interpretation. So this would now be something in three-dimensional space, and we have three vectors that would go out in different directions here, or maybe different directions. So basically the geometric interpretation of this, if this was an invertible matrix, all these would be going in different directions. None of them would be collinear, and none of them would be combinations of one each other. And theoretically, if this was invertible, you could access any point in this 3D space as a combination of these three vectors. But we don't have to really think about that too much. All we have to think about is one of these columns of this matrix a combination of the others. And we see that if we kind of look a little bit, we see that the third one is just the first and the second one added together. So that's 1 times the first one plus 1 times the second one equals this third one here. So we know that it is not dependent because one of these vectors is kind of going into the same line, or is kind of redundant in a way. So, and just kind of one more intuition thing here, when we have one vector here which is dependent on the other two, we have two linearly independent. These two are independent. And that means our span, instead of a line, is a plane in 2D space. But I won't talk about that too much. But all we have to tell is that this third vector is a combination of the other ones. So let's take a slightly more subtle example, maybe saying if the second column was maybe, I don't know, 10, 14, and 6. This is maybe a little more subtle of an example. And now we see that the reason why this one is uninvertible, and the reason why the columns of this are dependent, is because the second column here is 2 times the first one plus 1 times the last one. You see that if this is times 2, this becomes 4 plus 6 equals 10. This times 2 equals 6 plus 8 equals 14. This times 2 plus 4 equals 6. So this second one is dependent, and these two are the only ones that are linearly independent. And this again would have a span of a plane. But again, this would not be invertible, and that's the important thing to remember here. So if the columns of a matrix A are uninvertible, if the columns of a matrix A are some combination of one another, that means that in this geometric view, the span of those vectors, or those columns of A, is not the complete space, and is either some line or some lower dimensional thing inside of a higher dimensional area. Again, like I was mentioning, a plane inside 3D space is a lower dimensional thing, so anything outside of that plane you won't be able to reach with their span of vectors. So because of that, and because when these columns are dependent, that means you don't have a span of the entire space, and that means any right answer which is in that span of space will have an infinite amount of values. So if we have some right answer x in the span in this plane, there's an infinite combination, infinite amount of x and y values, so that we could combine these three vectors. So it would be something like this, right? All three of these would be in the same plane. There's an infinite amount of combinations of these three vectors that can get us to this point. Similarly, how there's an infinite amount of combinations of x and y, an infinite amount of values of x and y that allow us to get to this point, which means that there's an infinite amount of values of the vector x, which means finally, because of this, since x cannot have infinite values, or more than one value really, then the inverse can't exist. That's kind of the train of thought, and if it's a bit much, then that's normal, because it is a bit much. But hopefully that makes sense. Feel free to watch this video again or consult sources that might be a little more comprehensive. But that's the general gist of it, and that's the general gist of linear dependence and span. So just as a recap, span is a property of a set of vectors. So the span of a set of vectors is the dimensionality of the points that can reach. So the best is if we're sitting in some n-dimensional space, Rn is kind of what you're looking for. That's the span you're looking for. And linear dependence or linear independence is if columns of your matrix are combinations of one another. And one more term that might show up is column space, which I briefly talked about. And column space is simply the span of the vectors that are the columns of your matrix A. So basically, the column space of this matrix A here is the same thing as the span of the vectors 1, 2, and 2, 4. And one thing that I very quickly mentioned at the beginning of this lecture, and I didn't really talk much about, is that if this point here, if you have a linearly dependent system and your right answer point is out here, that means your equations are inconsistent. And that's just one more thing to state here. So for example, if you had 3 and 5 instead, so that means you'd have, your right answer would be over here, then instead of having infinite amount of values of x and y that get you there, there's actually 0. And that means your thing is inconsistent because that means there can't be any value of x that gets you there. Okay, hopefully that makes sense. I know it was a bit long, but it kind of had to be able to cover all these topics. But I'll see you in the next lecture. See you there.